The physical distance between star systems acts as a natural barrier, effectively keeping humanity quarantined within the Milky Way. Our closest habitable neighbor, the Andromeda Galaxy, sits 2.5 million light-years away from Earth. This timeline shows the scale of the travel problem. At a standard spacecraft speed of 28,000 kilometers per hour, reaching Andromeda would take 94 billion years. Even at the speed of light, the journey would still last 2.5 million years, orders of magnitude longer than a human life. To cross these distances, we cannot rely on propulsion through space. We have to find a way to bend the grid of space-time itself. Leaving the galaxy requires us to bypass the physics of traditional travel by manipulating the literal geometry of the universe. In 1935, Albert Einstein and Nathan Rosen identified a mathematical solution hidden in the theory of relativity. They described a bridge that could connect two distant points in the universe.
By folding a two-dimensional plane so points A and B touch, we puncture a tunnel through the middle. Physicist John Wheeler called this a wormhole, like a worm chewing a shortcut through an apple instead of crawling across its skin. While the equations allow for this bridge, building one requires a force capable of physically tearing a hole in the fabric of spacetime. Currently, only entities with the gravitational density required to warp spacetime this much are black holes. However, using a black hole as an entrance presents a major obstacle. Gravity here is so intense that anything entering is permanently trapped, creating a dead end. A functional tunnel needs a mechanism to expel matter at the other end. This led Igor Novikov to propose a theoretical exit, the white hole. This diagram shows the contrast in their mechanics. While a black hole's horizon is a point of no return, a white hole's horizon is a boundary of no admission. It would only allow matter and light to exit. The existence of white holes remains a subject of intense scientific debate. Some physicists argue they violate the laws of thermodynamics, while Stephen Hawking's theories on black hole evaporation suggest that the matter they swallow must eventually be spit out somewhere else. In 2006, astronomers observed a massive gamma-ray burst that defied the pattern of a collapsing star. It was a sudden, intense explosion of light that disappeared, leading some to hypothesize it was a rare glimpse of a white hole. Creating an interstellar shortcut would require us to harness the most destructive forces in the universe and align them perfectly into a stable system. In 2015, researchers transitioned mathematical concepts into a laboratory setting by successfully creating a magnetic wormhole. This diagram shows the experiment's results. Using a superconducting material, the team created a tunnel that allowed a magnetic field to travel from one point and appear at the other end while remaining invisible in between. If wormholes prove physically impossible to stabilize, the Alcubierre drive offers a different mathematical blueprint for travel. This drive contracts spacetime in front of a ship and expands it behind. The vessel stays stationary, effectively riding the distortion of space itself. A century ago, black holes existed only as controversial solutions to Einstein's field equations, predictions that remained unproven until we captured the first direct image. While our current equations describe these shortcuts, they also reveal massive obstacles, from energy requirements to thermodynamic constraints. The math has provided a map for leaving the galaxy, but we are still searching for the physics that makes the journey physically survivable.